Um, one idea is tractability, right? What does it mean? It means that I could do it, right? For many non-trivial problems, right? And you will see more of this in theory of comp, where you see it from a slightly different perspective, right? There's a natural brute force algorithm that searches every possible solution, right? Problem is it takes forever, right? And so it's not tractable in practice. Kind of one of my standard things is a traveling salesperson. You know what that problem is? You need to go to a bunch of cities, right? You need to visit all of the cities once. What's the minimum distance or the minimum cost if you're buying plane tickets, right? You could just try every possibility, right? What's the problem? There's a ton of possibilities, right? For traveling salesperson is n factorial, right? So that means that as your number of cities goes up, you're doomed. Does that idea make sense? So for many cases, right, you get brute force solutions that work. You say, oh, it's too slow. Computers are uber fast. For many cases, dumb brute force solutions actually work and work really well. I don't know if you ever like puzzles. Cryptarithmetic puzzles, 10 plus more equals money. I'm trying to. That'll probably work. And this is the standard example, right? You get something like this: 10 plus more equals money, and so you need to substitute every possible digit, right? And letters will always stand for one digit, and digits cannot be repeated, right? What's the dumb brute search algorithm for this? Assign every number to every letter, right? Or to every one of these letters, right? There will never be more than 9 letters, right? It is dumb. It doesn't look really cool on your resume. It doesn't get you, it's not AI or deep learning or anything like that. But on the other hand, you have 10 freaking digits, right? It works. It's 10 factorial. 10 factorial is nothing for a computer, right? You can solve it in your phone, right? So, depending on the algorithm, you may care, right? In this case, for almost, not every problem, for many, many problems, we have this brute force algorithm. That may not be intractable, maybe intractable, meaning it's not practical, it doesn't work for big n's, right? And sometimes they have big n's. What we want is something like, well, when the input size doubles, the algorithm, the running time of the algorithm doubles, right? Or maybe quadruples, but doesn't go by 1,000, right? Especially, you're worried about growth, right? So what if I quadruple it? If I quadruple it, then it should go double the double, as opposed to 1,000,000 times the double or something like that. Does that idea make sense? So we're talking about growth rate. For a polynomial time algorithm, when the input size doubles, the algorithm will grow by a constant factor, right? Why? What happens if we have did you know this? That is so horrible. Wasn't Google?
Google usually does that.
Y of n? Oh, I can do this. Doesn't like it with n's. Okay, they only do it with x's. What happens with this? As my x grows, right, I'm looking at this side, my y, my f of x, is gonna grow a lot more. How much more? If my x doubles, what happens to my y? It's not exponential. No, it's actually not that bad.
Logarithmically grows.
It goes 4 times 2 squared. Does that make sense? So the growth is bad, but not horrible, right? Right? If when my x is 2, my y is 4. When my x is 4, my y is 16. But when my x is 8, my y is 64-ish. 64, if I could actually manage to do that, right? So it is bad. It is not that bad. When I double, it goes by 4, right? What if my function is 100 times x squared? What happens? What happens to the shape of the graph? To the shape of the graph?
Same thing.
It's the same because Google scaled it, right? What happens? Well, it actually, this axis, the y-axis became a lot bigger, but it looks the same, right? It doesn't change the growth, right? Now, what happens if I do x cubed? So constants are not gonna matter, right? What happens if I do x cubed? Oh, I start getting, let me do x to the 4th. What happens to my graph? It is similar, right? Kind of the same. Actually, what's happening is that we are not seeing it. This is not actually flat. It's just that it grows so fast, right? That it looks kind of flat. With x cubed, you start getting positives and negatives, so my stuff inverts. And the shape is. So it grows a lot faster, but it's still not terrible, right? If my x doubles, what's going to happen to my y? 16 times, right? It's horrible. Could be worse. What happens when I do this? Vroom. Grows uber fast and basically, right, very close goes to infinity. It doesn't go to infinity, right? You could keep graphing if you had a bigger screen, but this is horrible. What happens if my x doubles? If my n doubles?
You lose your job.
I could lose my job. How much does my y grow? It's an unbound amount, depending on where I'm at, right? It could grow by gajillion times, right? So this is not polynomial. This is usually intractable. Intractable is really, we kind of appropriated it, but it really means it's not practical, right? I cannot do it. It's more than I cannot do it. It's I cannot do it, and I cannot just go to Micro Center and buy a faster computer to do it, right? It's not, there is kind of, especially the cloud has made a bunch of things that seemed intractable or impossible and practical, right? Just get 100 machines on AWS, right? I can do Hadoop. It used to be too slow, now it's not too slow, right? But this is, no, you're doomed, right? No matter how much money you put on AWS, right? You would actually use more capacity than AWS has in order to try to solve this if you use twice the X. Does that idea make sense? You're really, really, really doomed. That is the idea of intractability. So polynomial running time is usually good, not really. After n cubed, you're doomed. But below n squared, you're usually okay. You can usually deal with it by going to Micro Center and buying more RAM, right? By putting more machines on AWS or Azure. Above that, you're doomed. So there is this idea of polynomial time, right? Or poly time, it's really not polynomial, it's less than polynomial. When the input size doubles, the algorithm, or the f of n, right, goes up by almost a constant factor, c. A nicer, a more precise way to put it, an algorithm is polynomial time if there exist constants z0 and d0 for every input of size n, the running time of the algorithm is bounded above by cn to the d, right? Intractable is not polynomial, right? Efficient if it has polynomial running time. This kind of works in practice. It depends on the degree of the polynomial, but constants tend to not matter, right? Constants are the stuff that you go to Micro Center for more around. Many times we need to worry about worst case scenarios, right? How long does it take to sort something? Well, it depends. Maybe it's already sorted, right? And I just look at it. So I may have different algorithms. Most of the time, which one do I worry about? Worst case, because that means I lose my job, right? And Murphy's law guarantees that what's going to happen when you're demoing your work? The worst case, right? You know it, we all know it, it's going to happen, right? So you worry about the worst case. There's a couple of other ones. There is average and a couple of other things. And for some algorithms, usually not. There's exponential time algorithms that tend to work. We normally do them as, not quite this. I don't even know if any exponential algorithm is widely used in practice other than I'll run it and I'll stop somewhere, right? There is a couple of other things that we could do, right? We could analyze actually best case rather than worst case. The other ones that tend to be practical, right? The other ones that you would think, right? Best case sounds too optimistic. Is this idea of average somehow, right? There are actually different kinds of average-ish, right? Sometimes you get average on the input, right? That's the average case. So depending on the input that I have, my average is this. Right? Some inputs will be better, some will be worse, and then you need to decide whether you care about the worst case or not, right? Sometimes we find that the worst case for some algorithms is actually not that uncommon, right? So what can you do? Well, I could cheat and use probabilistic, right? It's like, well, I'm actually going to cheat and kind of, if quicksort works really bad for already sorted things, I can first shuffle them, right? So now it's not necessarily depending on the input because my algorithm is going to be probabilistic, right? But it's still the same idea of average, expected, right? Slightly different notion of expected. Do you guys see the difference? Cool. The cooler one, and this tends to be more for data structures, is amortized. It's the same idea of average, right? For something like a vector, right? What's the, how are vectors implemented, and what's the average case? Do you remember how vectors implemented? No. Cool. What's a vector?
An array that can expand.
An array that can expand, right? an array list in Java or something like that, right? How can I expand it, right? What's the most efficient implementation that you could think of?
Doubling it every time.
Well, right, just having the array, right? That would be cool. But, well, what happens? I cannot expand it, right? Well, I could reserve a few extra space, right? And keep going. Well, what happens when I run out of space? What do I have to do?
Create a new one and copy it.
I need to create a new one and copy it, right? So how long does that take? Forever, right? Takes order of n. Normally, how long does it take to insert one element in the array? Constant time, right? I just increment my max or my num elements or something like that. How long does it take if I have to copy that thing?
And
Forever, right? Order of n. It's not forever. It's actually not that bad, but forever each, right? So what's my worst case? Horrible. Order of n, right? But it's still this idea of, no, that's actually not going to happen. So we average it over all the calls, right? So we amortize it, like paying interest, right? Amortizing your debt. So for all these 100 inserts that were constant, right? I save a little bit of time and I put it back on this one that took forever. Does that idea make sense? And that's a way of justifying bad ideas. Now, that's a way of justifying algorithms that are efficient in one sense, even though the worst case may suck.
in that example, you were saying that O of n is terrible, and I've never really heard O of n being necessarily bad for an algorithm. So
Well, it's more when you're inserting something, right?
yeah,
When you're probably going over it a million times.
yeah.
So that's what makes it terrible.
Okay.
Compared to O of 1.
Mhm.
Compared to a constant, right? O of n is terrible. Does that idea make sense? And so the amortized analysis would say, well, yes, the worst case is horrible, but over all the cases, the average-ish is good. Does that make sense? It's kind of another way of doing average. And so we have these three different ways of average. One is probabilistic, the other one is amortized, the other one is actual average over all the possible inputs. Does this idea make sense? Yes, close enough. There is some other possibilities, but why does it matter, right? As my n grows, right, this stuff can grow obscenely, right? Order of n, my n grows, and this will probably be, right? For a modern computer, it's not a big deal. Depends on the constant, but let's assume that it takes about a second to do 1,000,000, so less than that is, right? N log n, and log is a horrible thing in math because everybody uses different logs. It doesn't matter because they are attached by a constant, right? They are related by a constant. Which log do you use in math? God, horrible people. Which log do you use in calculus?
Natural log.
Natural log, which is log base e, and e is a horrible number that's not rational, right? But it happens to kind of work without constants for calculus. Normal people, when they think about logs, scientific notation, right? You do base 10, because we tend to have 10 fingers, unless you use power tools. In computers, what log do we use? Base 2. Why? Because we have 2 fingers. No, because we have 2 digits, right? That's so for the most part here when we do log, we mean log. But, n log n is still, right? What's the log of 1,000,000? Log base 2 of 1,000,000.
2 to the 10.
No. 2 to the 10 is what? You're close. Okay, powers of 2.
Oh.
2, 4, 8, 16, right? What's 2 to the 10? That's the one that you need to remember. You remember 2 to the 8 because it's 256, right? 2 to the 10 is 1,000-ish. is 1,024, right?
2 to the 20 is a million.
2 to the 20 is a million-ish, right? So it's just 20 times, right? So it's maybe 10 seconds, but 100K is almost nothing, right? Because the log is going to be actually and a little bit more than 10. They're doing something weird here. N squared, right? What does it make my times, right? We assume some constant, right? Small n's, I'm still within a second, right? When I start to do big n's, I go from 1,000, which is 1 second. 10,000 is going to take me 10 squared, so 100 times more. So about a couple of minutes, right? 100,000 is going to take me 100 times more, right? I just multiply by 10 and multiply by 100, right? Because I'm squaring. So about 3 hours. And then a million would take me about 12 days. Not something that you want to do at work, maybe something you want to do for your thesis, right? Okay. If I get to n cubed, what happens, right? For 10K, I'm going to try to do this stuff. For 10K, I have 18 minutes, right? But for 1K, I have 18 minutes. For 10K, takes me 12 days, right? The same as a million for the other guy. But for 100K, it takes me 32 years. Not even your dissertation, right? And above that, right, takes me forever. And this kind of ends up, when you start going more, right, as you go to exponential, this becomes, there's no way that you're going to do it, right? 1.5 to the n. For only 100, you get 12,000 years. 2 to the n would take you 10 to the 17 years. I don't even know what's the right word for that. And n factorial is actually higher than 2 to the n, I think. Higher in this sense. And so it would take you, even for 30, would take you 10 to the 25 years, right? And you can do a million in a second, right? So if something's size of n factorial, you're doomed. You know that you're not gonna, that algorithm is impractical, it's unfeasible, is not good, right? Does that idea make sense? That's why this stuff is important, right? What do you do when you have algorithms on the lower end? When you have n log n and n squared and things like that, right? What do you do in here? You optimize, right? You try to make the constants go lower. You try to make it so that you only need a septium rather than a 90th or whatever, right? Core i5 instead of a Core i7, right? What happens when you are here?
You need to find new algorithms.
You're doomed. You need to find new algorithms or adjust your life goals, right? I'm not going to find an optimal thing. I'm going to find one that doesn't terribly suck, right? Those kinds of things. And that's what we do, right? So let's talk about it here. Oh, it's omega, not theta. Sorry. Theta is the other one.
Okay.
I can never remember those things because big O notation, right? T of n is order of f of n, big O of f of n, right? The big O is kind of less than, right? So if there are constants c greater than 0 and n0 greater than or equal to 0, such that t of n less than or equal than c times f of n for all n greater than n0. So basically, if we get a high enough n, right, we are going to be smaller. Does that make sense? Smaller, right? High enough and a constant, right? And we're discarding constants because just get a Core i7 instead of a Core i5. And that deals with constants. Does this idea make sense? If you remember, most of the sorting algorithms, right, are order of n squared. What happens if we have something like this? T of n is 32n squared plus 17n plus 1. It is order of n squared. Why? Well, because it's only a constant, right? And as n grows, what happens to that 17n?
Becomes insignificant.
It doesn't matter, right? So T of n is order of n squared. Since big O really means less than or equal, it's also order of n cubed, and also order of 2 to the n, and also order of anything you can think of that's much higher than n squared. Does that make sense? It's still less, right? But it's not order of n or order of n log n. Sometimes you get comparable things. Most of the time you get comparable things, and so you can sort them. We tend to say insertion sort makes order of n squared, compares, right? I tend to use it for the other one. Different books actually make use slightly different. It's not the letters, they use different order of means the other one. An alternate definition is T of n is order of f of n if the limit when n tends to infinity of T of n over f of n is basically our constancy, so it's less than infinity. I tend to use this definition. To me, that's the definition, right? Order of f of n is a set of functions, right? So we should write T of n is in order of f of n, and use this set thing, but we normally say T of n equals order of f of n, right? Normally, the domain of f of n, so that is what can go in n. The data type for n, if you're doing it programming, is the natural numbers, right? 1, 2, 3. But sometimes you have different things. We assume, because of reality, when we are talking about big O, that the functions are non-negative, right? Would be really cool if something would actually give me back time, but we haven't figured that one out. If you have done math, this will feel like a hand-wavy class. This will feel like we're abusing notation, and we will be. But you have to still, right? It's not just, oh, I can put whatever and it will work, right? So it is okay to abuse the notation, not okay to misuse it. Big omega is the other way around. Wait, this is, yes, that's omega, right? Big omega is the other way around, right? So big omega, T of n is big omega of f of n if there are constants such that T of n greater than or equal to C times f of n, right? So it's the other side of the inequality.
So if two equations have the same order, they can be the E, I'm not sure what that
yes.
is. They can be that, they can be omega, and they can be O to
Wait,
each other.
but the E is
Equals? But the other two have
the E is not
greater
equals,
than.
the E means in. This is a set,
Mhm.
this is a set,
Mhm.
this is an element. and this weird symbol is in,
Okay.
like set membership.
Yeah.
So, yes, given that the big things are greater than or equal, right? I think the smaller ones are without the equal. But big things are greater than or equal, so there could be functions that are both big O of each other and big theta of each other, right? Does that make sense? If f of n is big O of g of n, then g of n is big omega of f of n. But there could be ones that are both, and that is big theta. That's the one that you normally want, right? That means it's there is two constants, and you're always above one and below the other. Or, right, another way of putting it is you are big O and big theta. They are big O and big theta of each other, right? One will give you one constant, the other will give you the other constant. Does this make sense in a hand-wavy way? The exercise, assignment 1, will force you to actually use the definitions and manipulate it mathematically so that it will not just make sense, but really make sense. Does this idea make sense? All this stuff. Cool. If the limit when n tends to infinity of f of n over g of n is equal to a constant, then f of n is omega of g of n, right? And if the limit is 0, then f of n is O of g of n. It's a sufficient but not necessary condition. There is a couple of interesting things, right? First of all, if you have a polynomial, right, all that matters is the highest degree, right? And that's basically because the limit is a constant, which is a, the one for n to the d, right? So basically, all that matters is the last. If you have n squared plus n, the n becomes not important as n squared grows, right? So only the highest degree of a polynomial matters when you have polynomials. You don't have to say order of n squared plus n. You say order of n squared, right? Isn't that cool? Given that logarithms are related to each other by a constant, right? Order of log a of n is the same as order of log b of n, right? For this and other one is actually important. Logarithm of n is lower than any polynomial, right? So for every d greater than 0, log of n is O of n to the d. Right. So if log of n is smaller than n squared, is smaller than n, is also smaller than square root of n, right? Does that make sense? Logs are amazing. If you can make them, they are really, really cool. And exponentials are horrible, right? So for every number greater than 1, any polynomial is going to be lower than that number to the n. Right? Exponentials are the ugliest thing you can. And that is why we tend to say things like, oh, it's okay because it's polynomial, right? Or it's horrible because it's exponential. This math explains why, right? we could have more than one variable, right? And actually, that's not the typical usage, but that's okay. Well, yeah. And what would happen in our definition is that we would have more constants, right? More M0. We'll have N0, M0, and however many letters you have, right? So we tend to use stuff like takes order of n plus n. When you have two numbers that size you, right? We will talk more about this in next week, but linear time, some common running times, right? Linear time, we have order of n, right? Running time is proportional to the input size. It takes however long per thing. Stuff like finding the max in a non-sorted array, right? I have to go look at every element, right? And so it takes me about n. Depending on your algorithm, they actually did the right way. They start, well, the right and the wrong way. They didn't do the first one, right? Let's see, you say the max is the first one, then get through the other ones. What's the only problem with this? It's a notational problem. Starts at 2, why?
What array starts at?
Because they think that the array starts at 1. Normal people start at 1. Every programmer starts at 0. After your brain has been warped enough by C, you start at 0. But merge, right? How long? And many times also, you get what's my size? What are my things? For merging two lists, right? Merging two arrays, what can I do? How long does it take? Well, it takes about the size of both lists, right? Because I can just keep track of what's the current bigger one, right? I need extra space. I need another place to copy it, but it takes me the size of both lists, right? And here, I can decide what's my notation gonna be, right? These things are the same thing, so I can just say n, where n is the sum of both, right? Or I could say order of n plus n, or n1 plus n2, or something like that, right? But normally here I would say order of n, because they are the same, almost the same number. N log n tends to arise on divide and conquer algorithms. Actually, we have log n, right? It's not here. What's our log n example? You remember an algorithm that runs in logarithmic time? Quicksort doesn't. All the sorts do n log n or n squared.
Binary search?
Binary search, right? You remember binary search? I'm thinking of a number between 0 and 100. You try to guess it. I tell you high and low. What would you guess?
50.
50, right? I tell you high, then you go 75, and then you keep adjusting. That's binary search. Right? You played that as a kid, maybe, if you were a kid. That's log n, right? And so binary search arises in many times. For many kinds of things, you can just, I'll keep it sorted, and then I'll do binary search. And other ones do, other data structures tend to do log n, like searching in a binary search is log n, right? Order of log n. N log n tends to appear a lot on divide and conquer algorithms. merge sort and heap sort do n log n. Merge sort is just merging, right? So you first think of the array as containing a bunch of smaller arrays of size 1, and you do a merge on them. So now you have half of the arrays, they are all size 2, and you merge again on top of the previous memory, right? Now you have arrays of size 4, and then size 8, right? Each one of merging the whole thing takes you order of n, right? And then you do that log n times, because you keep doubling your size. That gives you n log n. Heap sort, which we'll probably talk more, just because heaps are cool, does the same kind of stuff with a heap. There is a bunch of algorithms that involve, an easy way to do it is just sort and then do whatever, right? How do we find duplicates in a list? Sort first and then go finding the duplicates, right? So they are order of n log n because you have sorts. In this particular case, the largest empty intervals, right, is again an n log n, because first you sort, right, the times, and then you find the largest interval between two. So n log n tends to be sorting-ish. The best algorithms we know for sorting are n log n. Which ones are the best algorithms for sorting? Define best, but which ones are the best algorithms for sorting?
The ones that are
O of n? Do we have O of n algorithms? As long as you cheat in your notation, yes, we do. Those tend to not be practical. Quick sort. What's quick? We'll talk about what. Radix sort, but it's only true if you don't count the length of the thing, right?
But you can't solve the constants when you never mind.
Yeah. It's a cheating way. It's like, oh yeah, as long as you have tons of duplicates, or as long as you don't really count that, as your n grows, the size of your string would grow, unless, or you'd have tons of duplicates. But, so radix sort, yeah, I know, we say that it's linear, but it's not quite true. Quick sort, right? And yeah, merge sort and heap sort. Merge sort sucks because it requires extra memory. Heap sort is actually fairly nice, and it's guaranteed to be n log n. Quick sort is almost always n log n, but what's the worst case? N squared, and that makes it fun, right? Many times we do quick sort. Some others do heap sort. Depends on how brave you are. N squared tends to arise in matrix, right, stuff, but also in get all the pairs of things and do something, right? Find, given a list of points in a plane, find the pair that's closest to each other, right? Or go find, go do match.com, right? Compare every person, right? Am I off my time?
Yep.
6:15-ish. Okay, cool. Then next week we will go over this a little bit, and then we'll go over basically this stuff for more algorithms and data structures. You do have assignment 1 that is due sometime soon?
Sunday.
This Sunday.
So just making sure, like a PDF sent to you, anything that you can.
A PDF would be great. A PNG is acceptable.
Okay.
I was gonna say, can we write it and convert it to PDF?
Yes, write it, take a picture of your phone. As long as I can read it, it's good enough.
Okay.
If you can scan it, that would be great. If you use LaTeX, I'll be eternally grateful, but as long as I can read it, it's good enough. I can never remember which class ends at 15 and which one ends at 45. Go stop this thing.